Welcome to The Explainer. Today, we're diving into a real planetary cold case. For years, we thought the story of Mercury was, well, pretty simple. It's shrinking. But it turns out there's a huge twist. A hidden force has been scarring its surface, and we're just now starting to figure it all out. So, when you think of Mercury, you might picture this smooth little ball that's just shrinking. But that's not the whole story. Its surface is absolutely covered in these massive cliffs. And the real mystery we're digging into today isn't just why they exist, but how they got these really weird sideways scars. And look, we're not talking about some small ridges here. These things are massive geological features. Some of these cliffs, they're called lobate scarps, are over a kilometer high. That's taller than pretty much any cliff here on Earth, and they can run for hundreds and hundreds of kilometers. It's just dramatic proof that this planet has been under some serious stress. All right, so to crack this case, we've got to start by looking at the crime scene itself, the evidence that's literally written all over Mercury's wrinkled face. These are the clues, right? Left behind by some incredibly powerful forces that have been shaping the planet for billions of years. So what in the world is a lobate scarp? Well, the easiest way to think about it is like a planetary wrinkle. Imagine the planet's crust getting squeezed so hard that one part just cracks and gets shoved right up and over the piece next to it. Geologists call that a thrust fault, and it's a dead giveaway that some huge compressive forces are at play. And for decades, the main suspect here seemed pretty obvious. It was just the planet shrinking. You see, Mercury has this absolutely enormous iron core, and it's been cooling down ever since the planet formed. As that core cools, it contracts, right? So the planet's crust has to shrink down to fit. That squeezing action would totally create the wrinkles, those lobate scarps that we see all over. Case closed, right? Well, not so fast. Okay, let's dig into the case of contraction. Because when scientists really started looking closer at the evidence, they found some clues that just didn't add up. The simple shrinking planet theory couldn't explain everything they were seeing. And this is exactly where that simple theory starts to fall apart. See, if Mercury was just shrinking uniformly, kind of like an apple wrinkling as it dries out, you'd expect the crust to just buckle straight up and down. But that's not what we're seeing. The observations show the ground isn't just being pushed up, it's also being pushed sideways. It's this weird oblique slip movement. Think about it like this. It's not just a simple squeeze, there's a grind to it. And that sideways motion, that's the one thing that simple cooling just can't explain on its own. So, that leads us to the big question, doesn't it? If our prime suspect, the planet just shrinking, doesn't have the whole story, then there must be an accomplice. What other force out there is powerful enough to actually twist the crust of an entire planet? And that brings us to our new lead, a gravitational twist. The new suspect in our lineup points to Mercury's closest, most massive neighbor, the Sun itself. You see, the Sun's incredible gravitational pull isn't some constant, steady thing. It actually ebbs and flows, creating this powerful twisting force we call tidal stress. Now, I know when you hear tides, you're probably thinking about our oceans, but this is a tide in solid rock. It's mind-blowing. As Mercury zips around the Sun, the star's gravity is literally deforming the entire planet, stretching it and squeezing it. This whole process creates a ton of stress inside the crust. And we're not talking about a gentle squeeze here. It's a powerful cyclical force. And it all comes down to a few really interesting details about Mercury. Okay, so first up is Mercury's orbit. It's kind of weird. It's not a nice, neat circle at all. It's a really stretched out oval or an ellipse. This is called high eccentricity, and what it means is that during its 88-day year, its distance from the Sun changes a lot. When it gets in close, that gravitational pull from the Sun is super strong. When it's far away, it's much weaker. And that constant change, that's what's driving this tidal stress. And this right here is the last really critical piece of the puzzle. Our moon, it's tidally locked. It always shows us the same face. Mercury? Nope. It spins in this really peculiar dance. It's called a 3-to-2 spin-orbit resonance. All that means is that for every 2 trips it makes around the Sun, it spins on its own axis exactly 3 times. It's a very specific rhythm. And because it's always spinning like this, that tidal bulge, the part of the planet that's getting stretched out by the Sun, is constantly moving across the surface, stressing out different parts of the crust as it goes. So, to see if this new theory held any water, scientists did what any good modern detective would do. They ran a simulation. They built this incredible computer model of Mercury, but not just the Mercury of today. No, they went back in time, modeling the planet as it was billions of years ago, back when these giant cliffs were actually forming. And what the model spit out was fascinating. It showed that way back in Mercury's past, these tidal forces were way, way stronger. Like today, the planet is dealing with tidal stresses around plus or minus 15 kilopascals. But billions of years ago, with a wonkier orbit and a different spin, those stresses could have hit plus or minus 40 kilopascals. That's more than double what it is today. So a much bigger force was definitely at play. But, and this is a big but, there's a twist. Even at 40 kilopascals, that's not nearly enough of a squeeze to crack solid rock on its own. The main force breaking the crust is still the whole planet shrinking. So this tidal stress, it's not our main culprit after all. It kind of feels like our new suspect is just too weak to have pulled off the crime. Or is it? So this brings us to the final act of our little mystery. If the tidal stress can't actually make the crack, what if it could influence the direction of the crack? What if it wasn't the main culprit, but the accomplice that steered the damage being done by the planet shrinking? So, to figure this out, the researchers did something really clever in their model. They basically created a virtual crust that was already super stressed out, right on the verge of breaking from all that shrinking. Then, they layered on the tidal forces to see which way the fault would want to slip. And the results? Whoa! It was a complete night and day difference. Okay, so let me break this down. If you're standing on one side of a fault line, right lateral slip means the other side moves to your right. Left lateral means it moves to your left. Simple enough. What the model showed was that if Mercury was tidally locked, like our moon, the faults would have a right lateral slip. But for a spinning Mercury, the model predicted a clear, undeniable preference for a left lateral slip. The planet's spin literally reverses the direction of the slip. It's a huge deal. So, the moment of truth. What happens when we look at the actual real-life faults on Mercury, like that huge one called Grifo-Rupes? What do we see? You guessed it, left lateral slip. It's a perfect one-to-one match with the model for a spinning Mercury. The evidence on the ground lines up exactly with the simulation. And there it is. We found our accomplice. Those giant cliffs on Mercury weren't just from a simple shrinking process. Yes, the planet was definitely contracting, but at the exact same time, it was being twisted by the sun's gravity. And because Mercury was spinning, that tidal twist basically steered the faults, guiding them to slip sideways in that very specific left lateral way. It wasn't one or the other. It was two incredible forces working together this whole time. It's such an elegant solution to a mystery that's been around for decades, you know? It shows how the seemingly subtle, cyclical force can leave such a massive, permanent scar on a planet over billions of years. And it really makes you wonder, right? What other amazing secrets are planets all across our solar system, and even beyond, hiding in the tiny details of their spin and their sway?